Hello, students, I'm Gan Xiao, the main lecturer for this course. Today, we will continue learning about the thermal motion of polymers. First, let's look at the learning objectives for this lesson. First, skills objective, recognize the physical states of polymers. These states vary mainly with temperature. Classify temperature deformation curves by polymer structure. Second, knowledge objectives. First, understand the physical states of polymers. Second, understand the physical meaning of temperature deformation curves. Third, quality objectives. Develop the ability to analyze and solve problems. Foster the habit of using theory to guide practice. The physical states of polymers depend mainly on temperature. The temperature deformation curve is also called the thermomechanical curve. It describes the molecular motion and mechanical behavior of polymers at different temperatures. The different mechanical states of polymers, we examine them over different temperature ranges. This allows us to plot the temperature deformation curve. So what is a temperature deformation curve? With the loading condition fixed, a constant external force is applied, which produces a corresponding deformation. This deformation varies with temperature. A constant external force is applied to the polymer sample, and it is heated at a constant rate. The resulting curve shows deformation as a function of temperature. We call it the temperature deformation curve. It is also called the thermomechanical curve. By polymer structure, there are two main types: A. Temperature deformation curves of linear amorphous polymers, and B. Those of crystalline polymers. The typical temperature deformation curve for amorphous polymers is shown in the figure. The horizontal axis is temperature, and the vertical axis is deformation. Please note that in different temperature ranges, the trend of deformation with temperature differs. At relatively low temperatures, deformation increases slowly with temperature. Once a certain temperature range is reached, the deformation rises sharply with temperature. After that sharp rise, it changes more slowly. And after another temperature range is reached, it increases again. Let's zoom in and take a closer look. The temperature deformation curve of amorphous polymers looks like this. There are two regions of abrupt change, called transition regions. In the lower temperature range, the polymer behaves as a rigid solid. A rigid solid has high hardness and a high modulus. As the temperature continues to rise, after this transition region is passed, the polymer becomes highly elastic. Under a small external force, it can undergo large deformations. At the same time, within this range, as the temperature changes, its deformation varies only slightly. And when the temperature rises further, the polymer enters the viscous flow state. The higher the temperature, the lower the viscosity. So the deformation increases sharply with temperature. The states corresponding to these three regions are called the glassy state, the rubbery, high elastic state, and the viscous flow state. At lower temperatures, that is, the glassy state, in which the polymer behaves as a rigid solid, only very small deformation occurs. This small deformation essentially follows Hookean elastic behavior. But when the temperature rises into a certain range, that is, above Tg, the polymer enters the rubbery, high elastic state, and its deformation increases significantly. In this range it reaches a relatively steady level. The material behaves as a soft elastomer. If the temperature continues to rise within this range and exceeds the viscous flow temperature Tf, its deformation changes very little. As the temperature rises further, the amount of deformation gradually increases again. Eventually, it becomes a viscous, flowing liquid, which is called the viscous flow state. These are the three mechanical states of polymers. The three mechanical states correspond to three different mechanical properties. In other words, polymers exhibit three different mechanical behaviors. In the glassy state, the material is a rigid solid. In the rubbery state, it shows rubber-like characteristics, with pronounced elasticity. and in the viscous flow state, it behaves as a viscous liquid. Thus, across different temperature ranges, we observe three distinct mechanical states. This is a macroscopic manifestation. We need to analyze it more closely. Behind these states, which motion units are actually responsible? Because each polymer motion unit has a different temperature range over which it can move. And this, in turn, determines the properties the polymer exhibits in that range. First, below Tg, chain segments cannot move. Their motion is essentially frozen. Only conformational changes are achieved by chain segment movements caused by internal rotation about single bonds. Thus, polymers essentially cannot undergo large-scale conformational transitions. At this stage, segmental motion is essentially frozen. However, motion units smaller than a chain segment, such as side chains, side groups, and small repeat units can still move. Mechanically, the strain is small, 0.01%, 1%. High modulus, 10 to the 9th to 10 to the 10th pascals. Short relaxation times, and purely elastic behavior. Polymers that are glassy at room temperature are typically plastics. For example, PMMA, polymethyl methacrylate, as well as atactic PS, polystyrene, and PVC, polyvinyl chloride. What about their service temperatures? They are all below the glass transition, that is, in the glassy state. When the temperature continues to rise and exceeds Tg, segmental motion begins, and chain segments become mobile. The molecular chain can then change its conformation through segmental motion. Segmental motion will produce significant deformation. Thus, under an external force, the molecular chain can extend from its original coiled state, leading to large deformation. However, the entire molecular chain does not undergo translational motion. This reflects the mechanical behavior characteristic, large deformation, which can reach 100% to 1000%. Low modulus, on the order of 10 to the 5th to 10 to the 7th pascals. Deformation is reversible, and the relaxation time is long. Polymers that are in the rubbery, high elastic state at room temperature are usually rubbers. If the temperature continues to rise and exceeds Tf, the entire molecular chain can also move, and the molecular chain is the largest of all motion units. When it becomes mobile, all smaller motion units can also move. Therefore, the mechanical properties exhibit large deformation, an even lower modulus, and an even larger strain. The viscous flow state corresponds to the processing temperature range. In this lesson, we covered the three physical states of polymers. Students, see you in the next class.